In Chapter 15, we're learning about some probability rules. Remember, we had a rule about disjoint events in Chapter 14. If two events are disjoint, which means that they have no outcomes in common, they cannot both happen at the same time, then the probability that one or the other occurs is the sum of the probabilities of each one. So, or comes from a union. Remember, this U means union, and that's what you should think of when you think of the word or. So the probability of A or B, A union B, is the probability of A plus the probability of B if A and B are disjoint. Remember, disjoint means the same as mutually exclusive. The general addition rule, which does not require that A and B be disjoint, says that the probability of A or B, A union B, is the probability of A plus the probability of B minus the probability of A intersect B, or A and B. The upside down U means an intersection which is and. So both. So if A and B are disjoint, then the probability of A and B is just 0, and we get the simplified addition formula that we had up here. But if they are not disjoint, if they're not mutually exclusive, then you have some intersection, and you need to subtract it off, not because you don't want to count it at all, but because you don't want to count it twice. You actually do want to count it once, because a union, an or, allows them to be both happening. A or B will allow A and B to happen, but this probability of A and B is included both in the probability of A and in the probability of B, and we don't want to double count it. So we have to subtract it off once, so that's only being counted once. This general addition rule is on the AP formula sheet, so you do not need to memorize it. If A and B are independent, remember that means that knowing that one of them happens does not affect the probability of the other one also happening. So we can mathematically show that two events are independent if we can show that that equation that I just circled in blue is true. That the probability of B given A is the same as the probability of B. That is called a conditional probability, the probability of B given A. That vertical line segment read as the word given, where the thing that comes after it is a condition that we are applying. So in other words, A and B are independent if the probability of one of them given the other one happening is just the same as the probability of the first one. So applying the condition did not change the probability. The probability of A does not, or the outcome of A does not influence the probability of B. Knowing that A happened did not change the probability that B also happened. So the probability of B given A, that conditional probability, is that formula there, the probability of A and B divided by the probability of A. So on the top is the probability of both of those events happening. On the bottom is the probability of the condition happening. Because when you're doing a conditional probability, the probability of B given A, you are narrowing your scope to only the times when event A happens. So that is now your sample space. That is what goes on the denominator of your fraction, is the probability of that condition happening. And then on the top is the probability of that condition and the other event you're interested in both happening. That formula is also on the AP formula sheet. So if A and B are independent events, the probability that both A and B occur is the product of the probabilities of each. The probability of A and B is the probability of A times the probability of B, as long as A and B are independent. If they're not independent, then we have the general multiplication rule, which is that the probability of A and B is either, and you can use either one of these, the probability of B times the probability of A given B, or probability of A times the probability of B given A. So multiply the conditional probability times the probability of the condition. All that is just a rearrangement of this conditional probability formula. If we take that fraction in that formula, we multiply both sides of that equation by the denominator of that fraction, then we get one of the versions of the general multiplication rule. So the general multiplication rule is not on the AP formula sheet by itself directly, but it's just a restatement, a rearrangement of this conditional probability rule, which is on the AP formula sheet. So one way to show, really we have two ways to show that two events A and B are independent. One way is to use the definition of independence up here, that compare the probability of the event with the probability of the event given the other event happening. If those two things are the same, the probability of the conditional probability, if it's the same as the probability without the condition, then those two events are independent. The other way to show that two events are independent is to show that this is true. The probability of A times the probability of B is equal to the probability of A and B, because that will only be true if A and B are independent. So keep those in mind when you're trying to show that two things are independent of each other. Those are your two possible ways to justify mathematically that those two things are independent. And you should justify it mathematically. What's a very common way to lose credit on probability questions? Not showing your work. You must show your work if you want to get credit on any free response problems involving probability. We're going to do a few examples here. What is the relationship between educational achievement and home ownership? A random sample of 500 people who participated in the 2020 census was chosen. Each member of the sample was identified as a high school graduate or not, and as a homeowner or not. Overall, 340 were homeowners, 310 were high school graduates, and 221 were both homeowners and high school graduates. We're going to create a two-way table and a Venn diagram that displays this data. So in the two-way table, you will have, it doesn't matter which one we put vertically and which one we put horizontally, but we could put high school graduate, high school grad, and not high school grad, and then homeowner and not homeowner. Sorry, it's difficult to write so small on my screen with this stylus, but you can tell what I wrote. So that divides us up into four different arrangements of these events. So what we're told is 340 were homeowners. How does that number fit into this table? Well, that's the total of all of the homeowners. There's 340 of them. 310 were high school graduates. That's the total of high school graduates, is 310. And then we're told 221 were both homeowners and high school graduates. So that number goes in this first spot of the table. 221 people are both homeowners and high school graduates. So knowing those three numbers allows us to actually fill in the rest of the table. What number goes to the right of the 221? We'll take the total, 310, and subtract out the 221. And you'll see that 89 people must go in that spot where they are high school graduates, but they are not homeowners. What goes below the 221? Take 340, the total for that whole column, and subtract 221. You get 119 people that are homeowners, but not high school graduates. What goes in that fourth box where it is not a homeowner and not a high school graduate? Well, if you add up those three middle boxes, the 221, the 89, and the 119, you get 429 people. But there's 500 people total. So if you subtract 500 minus 429, you'll see that there's 71 people left that go into that box. Because those 4 middle boxes all need to add up to the total of 500 people. Because those are the only 4 categories that those 500 people could find themselves in. So we could finish off these total spots here in a couple different ways. Add up 119 and 71 and get 190. You could also get the 190 by doing 500 minus 310. And then if you add up 89 and 71, you get 160, which you could also get by doing 500 minus 340. So there's 3 different things here that add up to 500. The 310 and 190, the 340 and 160, and then the 4 numbers in the middle all add up to 500 as well. So having it organized in a table like that will allow us to easily answer the questions about probability in the next section down below here. But we can also organize it in a Venn diagram. So these are just 2 different ways to organize the same information. You have one circle that might represent high school graduates, and another circle that would represent homeowners. And we know that 221 are both, so we can automatically put the 221 in the middle. But when it says that 340 were homeowners, that's the entire homeowner circle is 340. So if we want to know what fills in the rest of the homeowner circle, we have to take the whole homeowner circle, which is 340, and subtract out the 221 that's in the intersection. So we get 119 over here. Similarly, when it says 310 were high school graduates, that means the entire high school graduate circle is 310. So we subtract from that the 221 that's already in the middle, the rest of that section, the rest of that circle, is 89. And where does the number 71 go? Well, that is outside of both of the circles. Those are all the people that are not homeowners and not high school graduates. But do you see how we use the same 4 numbers that are in the center of our table on the left to fill in the Venn diagram on the right? Now we are prepared to answer B, C, and D down here. Suppose we choose a member of the sample at random. Find the probability that the member is a high school graduate. We can look at either the table or the Venn diagram. On the table, a high school graduate, there's 310 high school graduates out of 500 people total. So 310 divided by 500 gives us 0.62. How would we get that from the Venn diagram? We will total up the whole high school graduate circle, 89 plus 221, and we would divide that by 500. So that's 310 divided by 500. What's the probability that the member is a high school graduate and owns a home? Well, on the table, we would look for high school graduate and homeowners. That's 221. In the Venn diagram, it would be the overlap of the circles. 221 out of the total, 500. So 221 divided by 500 is 0.442. Remember, you're fine giving decimals or convert them to percentages or give me a simplified fraction. And part D, find the probability that the member is a high school graduate or owns a home. So from the table, being a high school graduate or owning a home means that you are a high school graduate or you own a home or both. So that would be, we could get it in a few different ways. We could just add up the people that are high school graduates and not homeowners. So that's 89 people, plus the people that are homeowners and not high school graduates, that's 119 people, plus the people that are both, 221. We add up those numbers and divide it by 500. We get 429 divided by 500, and that is 0.858. But we could get the same number if we utilize the formula, the general addition formula up here. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So, probability of being a high school graduate or owning a home, we could get that by doing the probability of being a high school graduate. That's 310 out of 500. Plus the probability of being a homeowner. That's 340 divided by 500. Minus the probability of being both, because we want to count it, but we don't want to count it twice. So the 221, is already counted in both the 310 and the 340. So we subtracted out once, 221 out of 500, so that we're not double counting it. So if you do that, you're going to get 429 out of 500, which is 0.858. The third way that we could have answered this question is to find the opposite of being a high school graduate or owning a home. The only thing that's left out are the people who are not doing either one. So the opposite of this is 71 people. So the other way we could have gotten this is to take 1 minus 71 out of 500. 71 out of 500 is 0.142. 1 minus 0.142 is 0.858. So there were 3 different ways that we could have gone about solving that problem. Next example. According to the National Center for Health Statistics, in December 2021, 30.6% of U.S. households had a traditional landline telephone, 97.6% of households had cell phones, and 28.9% had both. Suppose we randomly selected a household in December 2021. Using a Venn diagram, find the probability that the household has at least one of the 2 types of phones. Remember what I told you last class, if we want to find the probability of at least one, anytime you read that, it's the easiest way to do it is to find the probability of none and do 1 minus that. I'm going to leave you to solve this problem by yourself. Draw out the Venn diagram, put those numbers where they belong in the Venn diagram, and find the probability of at least one of the type of phone in that household. And then do the second part, find the probability that the household has neither type of phone. Draw out the Venn diagram, show your work. Next example. Each season, fans of the St. Louis Cardinals win 60-cent drinks from mobile on-the-run convenience stores if the Cardinals score 6 or more runs. In the 2022 season, the Cardinals won 93 of their 162 games and gave away 60-cent drinks in 57 of their 162 games. In 52 of the games, the Cardinals won and gave away 60-cent drinks. Let W be the event that the Cardinals win the game. Let D be the event that there were 60-cent drinks, which means they scored 6 or more runs. We're going to choose the Cardinals game at random. Summarize these data in a Venn diagram. Okay. We'll do this example together. We have wins. We have 60-cent drinks because they scored 6 or more runs. We know that in 52 of the games, they won and gave away 60-cent drinks. So 52 goes in the intersection. They won 93 of their 162 games. So the rest of the win circle is 93 minus 52. The whole win circle is 93. If you subtract off that intersection, then the rest of this is 41. What does the number 41 represent? It represents the games where the Cardinals won, but did not score 6 or more runs, so did not give away 60-cent drinks. The rest of the D circle are the times when they gave away 60-cent drinks, but they lost the game. They did not win. So they gave away 60-cent drinks in 57 of the games, but 52 of those games they also won. So that means there's only 5 games in this part of the Venn diagram where they lost the game but scored 6 or more runs. But remember, there's a fourth number we need to put in this Venn diagram, and it's the games where they did not win and did not give away 60-cent drinks. So if you add up the 41, the 52, and the 5, you get 98. There were 162 games total. If you subtract 98 from 162, there were 64 games where neither W or D happened. Okay, now that we've got the Venn diagram, we should be able to answer these questions. So part B, find the probability of W or D. Remember, W or D would mean W happening or D happening or both. So one way to do this is add up 41 plus 52 plus 5, the three middle numbers of the Venn diagram, and divide it by the total, which is 162. So 41 plus 52 plus 5 divided by 162 should be 0.6049 or so. If you prefer a fraction, you could say 49 out of 81. Again, either of those are fine, or write it as 60.49%. What about part C? Find the probability of W given D. Well, looking back at what that means, this conditional probability formula, we need the probability of both events happening and divide it by the probability of the condition happening. So we want the probability of, so the probability of W given D is the probability of W and D divided by the probability of the condition. The condition is the thing that comes after that vertical bar, so the probability of D. What's the probability of W and D? Well, that's the intersection of the Venn diagram. That's 52 out of 162. What's the probability of D happening? That's the entire D circle. So that's 57. 52 plus 5, 57 out of 162. So you're narrowing your scope to only the times when they gave away 60-cent drinks. So only times when D happened. And you are considering the outcomes when they also won. So that's 52 out of the 57. This is the same as 52 out of 57 if you flip that fraction that's on the bottom and multiply by the reciprocal. So all you need to do is either reduce that fraction or find a decimal for it, and you'll get 0.912. Part D asks, find the probability of D given W. Is that going to be the same thing? No. We're still going to have the probability of D and W on the top, which is the same as probability of W and D. But on the bottom, we're dividing by a different condition now, the probability of W. So, still 52 on the top, but on the bottom is the whole W circle, which is 93. So 52 out of 93 gives us 0.559. So E, are the events D and W independent? One way to show that they are independent or not is to compare a conditional probability with the probability if you remove that condition. So we have calculated both conditional probabilities already. We can pick either one and use either one. So if we just take the first one, the probability of W given D, what do we want to compare it to? We want to compare it to the probability without the condition, so just the probability of W. We want to see if those are equal. So the probability of W given D was 52 out of 57, or 0.912, 91.2%. Is that the same as the probability of W? Well, W happening was 93. They won 93 games out of the 162 games total. And 93 out of 162 is a fraction that reduces down to 31 out of 54. But it is 0.574 in comparison to the 0.912. Since those are not equal, those two probabilities are not the same, then D and W are not independent. Because what we did was we looked at whether knowing D happened changed the probability of W, and it did. Knowing D happened actually increased the probability of W happening. So D occurring changed the probability of W also occurring. That means they are not independent. Next example. In January 2010, the Kaiser Family Foundation released a study about the influence of media in the lives of young people ages 8 through 18. In the study, 17% of the youth were classified as light media users, 62% were classified as moderate media users, and 21% were classified as heavy media users. So media includes social media, but also listening to music, watching TV. Of the light users who responded, 74% described their grades as good, which was classified as A's and B's, while only 68% of the moderate users and 52% of the heavy users described their grades as good. According to this study, what percent of young people ages 8 through 18 described their grades as good? So you want the total percentage of people who describe their grades to be good. So there are really 3 different ways in which this could have happened. Their grades could be good. This is what we're interested in, is the probability they have good grades. The grades would be good if they were a light media user whose grades were good. So the probability of light and good. Or they could be moderate media users and have good grades. Or they could be heavy media users and have good grades. So we basically can break this down into those 3 different cases. And because all 3 of those cases are mutually exclusive, they cannot happen at the same time. It can't be a light media user and a moderate and a heavy one. Then we can add up those 3 probabilities to find the total probability of being good. But we were not given any of those 3 numbers directly either. If we want the probability of being a light media user and having good grades, we're going to need to take the probability of being a light media user, which is 0.17, and we're going to need to multiply it by the probability of having good grades if you're a light media user. That was 0.74. So this is an application of the general multiplication rule. If I want probability of both A and B happening, I can get it by multiplying the probability of one of them times the probability of the other given the first one happening. So the probability of being a light media user and having good grades is the same as the probability of being a light media user times the probability of having good grades if you are a light media user. Those were the numbers we were given, so we can multiply those two to get the probability of being both someone with good grades and someone who's a light media user. Similarly, for the moderate, 62% were classified as moderate media users, so 0.62. Multiply it by the probability of having good grades if you are a moderate media user, which is 0.68. And then the last one, plus probability of being a heavy media user, 0.21, times the probability of having good grades if you are a heavy media user, which is 0.52. I'll leave you all to do that multiplication and that addition and come up with the final answer. Did you get it? I got 0.6566. I hope you got the same thing. If you did not, either me or you typed it into our calculators wrong. So there you go. What percent of students with good grades are heavy users of media? So we need to figure out what that question even means. If you try to translate it into this into probability notation, you're looking for people with good grades who are heavy users of media. What percent of students with good grades? So you're only looking at people who have good grades. You want to know the probability that they are somebody who is a heavy user of media. Well, that's saying we're going to apply a condition of having good grades. And within that category of people with good grades, we are looking for people who are heavy users of media. So this is a conditional probability. How do we find this conditional probability? Well, using the definition of a conditional probability, we'll find the probability of being both a heavy media user and having good grades. And we'll divide it by the probability of the condition, which is having good grades. Well, we found that denominator already, 0.6566, assuming I typed it into my calculator correctly. And on the top is the probability of having good grades and being a heavy media user. Well, that is this part right here, heavy and good. So that's 0.21 times 0.52. So we had to use our answer from part A as the denominator for our answer of part B here. So I get 0.1663. Many employers require prospective employees to take a drug test. A positive result in this test indicates that the prospective employee uses illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of prospective employees use drugs. The false positive rate is 5%. The false negative rate is 10%. We're going to draw a tree diagram. A tree diagram is another way to visualize how the probabilities are working. So it's another good strategy for particular types of probability problems. So everybody's taking the drug test. A positive result indicates that the test is saying that they use illegal drugs. But sometimes there are false positives. So 4% of the prospective employees actually use drugs. The false positive rate is 5%. The false negative rate is 10%. So the first terms of our tree might be that they are a drug user or not a drug user, because everybody fits into one of those two categories. And we know the probability of both of those because we're told 4% actually use drugs. So I'm going to write that as a decimal here, 0.04. If 4% use drugs, that means 96% do not. Now, everybody is taking the drug test. So, for the drug users, they either test positive or they test negative. For the not drug users, they either test positive or they test negative. We're told the false positive rate is 5%. That means of the people who do not use drugs, 5% of the time they test positive. So I'm going to put 0.05 on that branch of the tree. That's among the people who do not use drugs, 5% are testing positive. The false negative rate is 10%. Those are the people who use drugs, but the test falsely returns a negative result. It does not detect that they use drugs. So we're going to put 0.1 on that part of the tree. But we know then how to fill in the rest of the tree. Because among the drug users, if 10% of the time they're getting negative results, then 90% of the time they're getting positive results. And that's a good thing. It's correctly determining 90% of the time that people use drugs. Among the not drug users, 5% of them are getting positive results. That means 95% of them are getting negative results. But what we want to do then is figure out the overall probabilities of the 4 different outcomes that can occur. So we can have a drug user who tests positive. What's the probability that we have a person who is a drug user and they test positive? We're going to multiply along those branches of the tree. The ones who are drug users and test positive. If we multiply 0.04 times 0.9, then we get an overall probability of 0.036 that somebody is a drug user and tests positive. Similarly, the probability that somebody is a drug user and tests negative will be 0.04 times 0.1. You multiply along those branches of the tree, get 0.004. Probability that somebody is not a drug user and tests positive is 0.048. The probability that somebody is not a drug user and tests negative is 0.912. That's the biggest category of all of your people. What do all 4 of those numbers add up to? All 4 of those numbers add up to 100%. Because those are the 4 different categories overall that one of these employees, prospective employees, could fall into. So the question for part A is, what percent of prospective employees will test positive? The probability of testing positive is going to be 0.036 plus 0.048. Those are the 2 ways to test positive. Be a drug user and test positive, 0.036. Be a not drug user and test positive, 0.048. The probability of testing positive, 0.036 plus 0.048. That is 0.084. 8.4% of the time, you're seeing a positive result. Part B, what percent of prospective employees who test positive actually use illegal drugs? So that is a conditional probability. We are only looking at the people who test positive. That's the condition we're applying. We want to know what percent of them use illegal drugs. What percent of them are a drug user. We need to then apply the conditional probability formula. And I'm going to leave you to set that up and solve it and find that probability.